Hey guys, this is the final part of the AQA AS Level Further Maths Specimen Paper 1. We're doing the last two questions, 11 and 12. I'm sure it's going to be a whole heap of fun. Let's do this. Okay, question 11. So, the equation x cubed minus 8x squared add cx add d equals 0, where c and d are real numbers, that's an important little bit, has roots alpha, beta and gamma. When plotted on an Argand diagram, the triangle with vertices at alpha, beta and gamma has an area of 8. Given that alpha is equal to 2, we need to find the values of C and D. So quite a tricky one, this one. So as I said, it is important that C and D are real. So if C and D are real, and alpha is a purely real root, that means then that beta and gamma have to be a conjugate pair. So we could say then, well, we know alpha is equal to 2. We could say beta is equal to J add I K, and then we could say gamma then is the conjugate of that, so J minus IK. Okay, so what else do we know? We know the sum of roots of a cubic. So the sum of roots is minus b over a. So here, this is minus 8 over 1. So for us here, that's 8. Now that then tells us that alpha add beta add gamma is equal to 8. More importantly, that tells us 2 add 2j. 2 add 2j is equal to 8, which leads us to j is equal to 3. So up to there we now know the real part of beta and gamma. Okay, so now that we know the real parts of beta and gamma, we can now go to our Argand diagram, which is going to look something like this. So alpha, we were told from the start, was equal to 2, so there's no imaginary part, so that's just a 2 on the x-axis. Now we know the real part of beta and gamma is 3. What we need to work out is the imaginary parts. Now remember, we know that the area of this triangle is 8. So we need to work out what we need this length between the top root and the bottom root to be. So I'm just going to make a little sketch of this triangle here. So we know we've got a height of 1. The area is base times height divided by 2. So from that we know that 8 is equal to the base divided by 2. Therefore, the base is equal to 16. Now, half of that length is going to be above the x-axis, half is going to be below. So that then allows us to say, well, beta can be 3 add 8i, and gamma can be 3 minus 8i. So now that we know our 3 roots, alpha, beta and gamma, we can now work out C and D. Okay, so probably the easiest of the two is D. Now D, the number at the end of the cubic, is the negative of the product of the roots. So D is minus 2 lots of 3 plus 8i times 3 minus 8i. So this will give us minus 2 lots of, well, 3 squared, so 3 squared minus 64i squared. Now 3 squared is 9. So minus 2 lots of 9. Now I squared is minus 1. So minus 64 times minus 1 is positive 64. So we got minus 2 times 73, which gives us D is equal to minus 146. Okay, then finally C is the sum of the product of the roots taken 2 at a time. What does that mean? Well, it means it's alpha, beta, add alpha, gamma, add beta, gamma. So we've got 2 lots of 3 add 8i, add 2 lots of 3 minus 8i, and then add the conjugate beta gamma, which we worked out up above was 73. So I'm not going to do that again. So we got plus 73 on the end. So we got 6 add 16i, add 6 minus 16i, add 73, and then that leads us to C is 85. Okay, question 12a. So a curve C1 has equation y is equal to f of x, where f of x is 5x squared minus 12x plus 12 over x squared plus 4x minus 4. The line y equals k intersects the curve C1, so that's going to be a horizontal line. We want to show that k plus 3 times k minus 1 is greater than or equal to 0. So, quite a big one. I'm going to run through the game plan before we actually get going. So the fact that y equals k intersects the curve tells us that there is a point where the horizontal line and the curve are equal, or there is at least one point where they are equal. Now, so we're going to set k equal to the fraction, and then we're going to be able to rearrange that into a quadratic that is equal to 0. Then, because we know that there is at least one point of intersection, at least means there could be one or two, because we're dealing here with a quadratic. So then we're going to think about what that means for the discriminant, in particular, if there are, if there is only one real solution, the discriminant would equal 0. If there are two real roots, then the discriminant is greater than 0. So we don't know how many points of intersection there are, but we do know there is at least one. There could be two, so the discriminant is going to be greater than or equal to 0. So that is where this inequality is going to come from. Okay, so let's do this. So the two things intersect. So first of all, we can say k is equal to 5x squared minus 12x add 12 all over x squared plus 4x minus 4. So what we want to do now is rearrange this so that everything is on the same side, and we got an equals 0. So we're going to multiply through by this quadratic on the bottom. So that's going to give us k x squared plus 4k x minus 4k, and that is equal to 5x squared minus 12x add 12. Okay, now we want to move everything from one side onto the other. So I'm going to move the stuff on the left, the stuff on the right to the left. So I'm going to take away 5x squared. So I'm going to have k x squared minus 5x squared. And I'm going to add 12x. So I'm going to have plus 4k x plus 12x. And then I'm going to subtract 12. So then we're going to have minus 4k minus 12. And that is all equal to 0. Okay, so now I'm going to factorise a bit so that we only have a single x squared term and a single x term. So we've got kx squared minus 5x squared. So we can factorise that to k minus 5 x squared. Then we've got 4kx add 12x. So we can then write that as add 4k plus 12 x, and then we can even factorise this last bit a little bit. So we got minus 4k minus 12. So to factorise that, I'm just going to put that as minus 4k plus 12. And again, that is all equal to 0. Okay. So now we know then that because there is at least one solution, then the discriminant is greater than or equal to 0. Now again, it's because we don't know how many solutions there are. There is at least one, but there might be two, so the discriminant has to be greater than or equal to 0. So remember, the discriminant is b squared minus 4ac. So b squared minus 4ac is greater than or equal to 0. So b squared is 4k plus 12 all squared. And then we've got minus 4 lots of k minus 5 times minus 4k plus 12. And again, we know that is greater than or equal to 0. So now we're going to want to expand this stuff. What would be really nice is if we could spot a common factor at all. So first of all, I'm going to sharpen it up at the end a little bit. So we've got 4k plus 12 squared now we got minus 4 times k minus 5 times minus 4k plus 12. So we got a minus times a minus, so this becomes plus 4 lots of k minus 5 times 4k plus 12 Okay, so that is greater than or equal to 0. We've now got a common factor of 4k plus 12. So we could factorise this a bit and say, well, we've got 4k plus 12 lots of 4k plus 12 at the start. And then add 4 lots of k minus 5. Okay, so now inside of the square bracket, we can simplify a bit. So we've got 4k plus 12 times Okay, so we got 4k plus 12. And then we've got add 4k. And then we've got minus 20. Okay, so we have got 4k plus 12 inside the square brackets. Now then we got 4k plus 4k, which is 8k. And then we got plus 12 minus 20. So that's going to give us minus 8. Okay, so that's all greater than or equal to 0. Now, both of these fractions have brackets have common factors inside of them. So this first bracket has a common factor of 4. So if we divide that away first, this first bracket becomes k plus 3. And this second bracket has a common factor of 8. So if we divide that away, we get k minus 1. And that is all greater than or equal to 0. And there it is. We've shown what we wanted to show. Good times. Okay, then A part 2 says, hence, find the coordinates of the stationary point of C1 that is a maximum point. So, we're using this inequality that we've just found out. Remember, this is the discriminant of that quadratic equation on the previous page. Now, let's think about what this means. So, when the discriminant, so if the discriminant is equal to 0, that means there is one real root. So here, the discriminant is equal to 0 when k is equal to minus 3 or positive 1. So those are the values for k that would lead us to one solution. So remember that y equals k is a horizontal line. So if this horizontal line is only hitting the curve at one point, then it's hitting the curve at the points where the gradient is equal to 0, so at the stationary points. So we can then say, therefore, there are stationary points when y is equal to minus 3 or y is equal to positive 1. So that's where our stationary points are. So let's take a look back at k plus 3 times k minus 1. Let's think about what that actually means. If we say y is equal to k plus 3 times k minus 1, then if we call the x-axis the k-axis for now, what this looks like is quadratic like that, where this point is -3 and this point is 1. Now, let's think about when there would be no solutions. So, if the discriminant is less than 0, then there are no real solutions. So here we can see when k is greater than -3 but less than 1, the discriminant is less than 0. So what that tells us is that there are no intersection points. So there are no intersection points for y between -3 and 1. So that means it has to touch the curve at a final point at y equals -3, and that doesn't touch the curve at all if we are moving this horizontal line up, and this horizontal line doesn't touch the curve again until we get up to y equals +1. Therefore, therefore y equals -3 is the maximum. So now we need to find the x coordinate of this maximum point. Okay, so to do that, we're going to borrow one of the equations from the previous page, which is going to be this guy here. So remember that at these stationary points, or at this stationary point, y is equal to k. That's the equation of the horizontal line. So what we're going to do is we're now going to, well, we know that y is equal to k, so we're going to sub k equals -3 into this guy. So let's change the colour. That's going to give us then -3 minus 5x squared. So that's going to give us -8x squared. 4 times -3 is -12. So that add 12 is 0. So the x term disappears. So too does the constant term at the end. So we get left with -8x squared is equal to 0. Therefore, x is equal to 0. So the maximum has coordinates 0, -3. Good times. Okay, then for 12 part B, we want to show that C2, which has equation 1 over f of x, has no vertical asymptotes. So 1 over f of x is 1 over this fraction. So it's going to be x squared plus 4x minus 4 over the other bit. So x squared plus 4x minus 4 over 5x squared minus 12x plus 12. Okay, so vertical asymptotes would happen if the denominator was equal to 0. So I'm going to say potential asymptotes when 5x squared minus 12x plus 12 is equal to 0. The reason that gives us asymptotes is because we would then be trying to divide by 0, which we can't do. So let's check the discriminant to see how many solutions this quadratic has. So b squared minus 4ac would be minus 12 squared, which would be positive 144 minus 4 times 5 times 12. So 4 times 5 is 20, times 12 is 240. So that's going to give us an answer of minus 96. So the discriminant is less than 0, so the denominator 5x squared minus 12x plus 12 is never equal to 0. So 5x squared minus 12x plus 12 is never equal to 0, which means no vertical asymptotes. Cool. Okay, and then the final part asks us to state the equation of the line that is a tangent to C1 and C2. So we know tangents of C1 are y equals minus 3 and y equals 1. Now remember, C1 is equal to y equals f of x. C2 is equal to y equals 1 over f of x. So when f of x is equal to 1, C1 is equal to C2, which is equal to 1. So the equation of a tangent is y equals 1. It's the only one it can be. Okay guys, that's it for the paper. I really hope it's helped. It's taken a lot of work. Good luck in all your exams. Take it easy. Take care.